Hello everybody and welcome again to Midas Civil Advanced Webinar Series. The topic of today's webinar is construction stage analysis. And through the course of the webinar, I would be dealing with the introduction, modeling features, construction stage analysis control, and finally the results. So the first question that comes in mind while doing the construction stage analysis is why the construction stage analysis is needed. So as you can see in front of your screens, this is the construction stage of a balanced cantilever bridge. And as all of us know that during the construction of a balanced cantilever bridge, it may have long unsupported cantilever section, which may induce forces such as negative moments at these sections. Also, we should know that in the final bridge profile, the structure becomes continuous, which leads to lesser negative moments at mid supports, and hence the construction sequence may lead to critical force effects, which may lead to shear and flexure failure during the construction stage analysis. Also, the time-dependent material properties play an important role in the segmental bridge construction, and hence the construction stage analysis becomes necessary. This is the flowchart of construction stage analysis in Midas Civil. First, the modeling of the structure is done. After that, we define the structure groups. After defining the structure groups and assigning elements to the structure group, we define loads under the load groups. We define boundary under the boundary groups. We generate stages and define the construction stage data in terms of element, boundary, and loads. And finally, we select the various options available in construction stage analysis control to run the analysis. This is how the construction stage analysis dialog box looks in Midas Civil. Let's first look the real scenario in which in the first step of the construction stage, the user can activate or deactivate elements, boundaries, and loads. The same applies to the last step, but when the user defines any additional steps, only the loadings can be activated or deactivated. Now I will take you to the program to show the construction stage definition dialog box. So we can give a name here and the duration. We can add additional step as I told you earlier. Here the elements are activated and deactivated, and the boundary tab, boundaries are activated and deactivated, and in the load tab, loads are activated and deactivated. We can activate the load either in first or last step or any additional step as desired. So the first and the basic principle in modeling the construction stages is to define groups. Three different types of groups need to be defined. The first one being the structure group, the second one being the boundary group, and the third one being the load group. The groups are important because you cannot activate or deactivate individual elements in a construction stage. You need to group them and activate them under a construction stage, and the same thing applies to load and the boundary groups. But here we should understand one thing, that the tendons need not to be grouped for activating or deactivating. Tendons are activated as loads, and I will describe that briefly during the course of the presentation. During the course of the webinar, I would also show you a model. This is the model of a spliced girder bridge. The girder bridge is constructed in three different stages. The stage one is the construction of concrete box girder, and while constructing the concrete box girder, temporary supports at the left and the right end of the box girder are provided. Here we will model the concrete box girder as a grillage model, and the self-weight of the girder and piers will be activated in stage 1. The stage 1 comprises of the construction of precast beams. The precast beams will be simply supported at between these two supports, this being the abutment support, which is the permanent support, and this being the temporary support or the fall support. At this stage, the beams will not be continuous because the deck will be casted in a later stage, and hence we will use the beam end release function to simulate the simply supported nature of the beams. Also, we'll activate the end supports. As I told you earlier, these are the abutment supports. We'll activate the self-weight and pre-stressing, and deck will be casted on the day 10 of this construction stage, and the weight of the deck will be considered for the analysis. And in the stage 3, the deck will become activated. It will become a structural component, and we will remove the scaffolding weight and wet concrete weight. The temporary supports will also be removed, and post-tensioning will be done. So now let me take you to the model. This is the spliced girder model that I have already generated. I have done the basic modeling. I have defined the materials and the sections. The section that I am using is a composite section for the precast girders. It comprises of a girder and a deck at the top of it. I have also defined several static load cases, and I will define the loads under these load cases later during the webinar. And I have also defined the tendons, tendon profile, which would be pre-stressed and post-tensioned tape. So now let's first talk about the element activation and deactivation process. While we activate an element in construction stage analysis, define dialog box, only the elements that become the structural components must be activated. The elements which are casted but still have scaffolding shouldn't be activated. The elements which are casted but have scaffolding would be included as a weight, and I will show you later how we can do that. So this is a typical example of how the elements are activated. First, we model the elements. We define them under a structural group, and then we activate that structural group in the construction stage in which it becomes the structural member of the structure. While activating the segment or an element, the user must enter the age of the element at the activation. The age is important to determine the time-dependent material properties that would be used for the analysis. So the clear question that comes to our mind is how to define the age. Here I have shown you a typical example that I will be using in my model. The deck is constructed, the deck is casted in construction stage 2, but the scaffolding will be removed 20 days after the casting of the deck. So the age of the deck on the first day of construction stage 3, when scaffolding will be removed, will be 20 days. So as I discussed before, that the element which is casted but the scaffolding is still on shouldn't be activated. So how we can consider the effect of that element? So let's say these segments on the left and the right are casted but they still have scaffolding. So what we will do in construction stage 8 on day 7, we will activate a load corresponding to the scaffolding and the element in construction stage number 8, as you can see, and on the first day of construction stage 9, when the element becomes the structural component, we will activate the element and we will deactivate the load. I have deactivated the load here because when we define the self-weight in Midas Civil, and as soon as the element is activated, the self-weight already takes into account the load of the element. So if we do not deactivate this load here, we will end up having duplicate loads for the element. Also, when we define composite sections and the deck and the girder becomes composite in different times, then we can model that with the help of composite section for construction stage dialog box. I would be using this dialog box in my model. So let's go to the model and see what elements have to be activated in what stage. So this is the model that I have already generated. Here you can see under the groups tab, I have defined 4 structural groups for structures. First being pier. If I go closer, you can see these are the piers, the 2 piers. This is the box girder, and on the left and on the right side of it contains the composite sections. So I will quickly assign structure group to the structures. I see I have selected the piers and the nodes associated with the piers, and I will use the drag and drop option of Midas Civil to define them under the structure group pier. Now I will select the box girders and I will define them under the group box girders. Now I will select the precast girders, but here I would like to tell you that the cross beams that I have made are made to provide the structure rigidity or stiffness in the transverse direction, because the deck will be continuous. And since we are modeling the deck as a composite section, so we need to provide the transverse stiffness with the help of cross beams. So I will select the cross beams. Here I will select that only the elements in the X direction must be selected, and I will select the corresponding elements. And as you can see, the elements except the cross beams have been selected. And now again I will use the drag and drop feature to assign them under the structure group PC girders. And lastly, I will select all the cross beams by using the section type, and I will assign them under the structure group cross beams. So as you can see, I have defined piers, I have defined box girders, precast concrete girders, and cross beams under different structure groups. Now I will generate the construction stages. So as I told you earlier, we will have 3 construction stages, each having the duration of 30 days. And I have generated 3 construction stages, each having the duration of 30 days. As I told you earlier, in the stage 1, we will construct the pier. I am providing the age of 30 days to the pier because it is constructed much prior to the construction of box girder, and the box girder has the age 7 when the scaffolding is removed. So I provided it an age of 7 days. Now I will activate precast girders, and they will have an age of 7 days again in construction stage 2. And finally, in construction stage 3, when the deck will be composite with the girder, we will activate the cross beams having the age of 20 days, as I told you earlier how this 20 figure came into being. So in a way, I have defined all the construction stages and all the elements related to it. Now I will define the composite section for construction stage. Since the deck becomes composite in CS2, so the girder is casted in construction stage number 2, and it becomes composite with the deck in construction stage number 3. I will provide the age, and we are ready. So we have defined the composite section for construction stage and the stages. Now we can see what elements will be activated. So as you can see in CS1, we have activated the piers and the box girder. In CS2, we have activated only the girders and not the deck over it. And in CS3, the deck has become composite with the girder and the cross beams also appear. But we have to define the weight of the scaffolding and the wet concrete in construction stage 1. So for that, I will define a load in terms of element beam loads, and I will define the load under the group deck plus scaffolding. I will select the precast sections using the section type selection bar, and I will assign this weight to these sections. So as you can see, I have assigned the weight of deck plus scaffolding here, and now I will activate this load on the 10th day of CS2. And how I get this value 10 is the duration of CS1 is 30 days. CS2 starts at 30 days, and after 10 days, that is at the 40th day, the deck is casted. So I will generate a step at the 10th day, and in the load tab, I will activate the deck and the scaffolding load at the 10th day. And in CS3, I will deactivate the load as I told you earlier. So now let's talk about the boundaries, activation and deactivation. As you can see here, while the construction of bridge is going on, it has been provided some temporary supports in form of steel trusses. You can model the temporary support in Midas Civil by activating it on the day it is applied and deactivating it on the day it is removed. This is the same typical manner in which we activate or deactivate a support. First, we define the boundary groups. We assign boundary groups to the supports, and then we activate the supports in the construction stage definition dialog box. One thing the user must understand while activating or deactivating the boundaries is that he should select original or deformed and when they should be selected. So original is selected. I will demonstrate that with the help of an example. As you can see on the left side, this is the construction stage of a balanced cantilever bridge, and if we assign the supports as an original option, Midas Civil will automatically apply a force in the upward direction to bring the structure back to the normal position because it has already deflected like this due to the dead loads. While if the user selects the deformed option, no such force is applied and the supports are applied at the deformed position of the structure. I would demonstrate the original option with the help of a video here. I think there is some problem in the video. Actually, this is the construction process of an ILM bridge, and when it reaches here, the bridge, these jacks will uplift the bridge and they will apply the original position of the supports. Also, with the help of the boundary activation and deactivation, we can apply the beam and releases. The beam and releases become very important in this scenario when in construction stage 1 the girder is simply supported, and in construction stage number 2 the girder becomes continuous because of the laying of the deck over it. Now I will take you to the model and I will show you what all boundaries have to be activated or deactivated. So this is the model. First, I will provide the supports to the pier and end abutments. So I will define them under a boundary group known as pier support, and I will provide it a rigid support. Now I will provide supports to the end of the abutments here. I will select the boundary group abutment supports. I have selected all the nodes here. Similarly, I will select the nodes on the right hand side. And I will apply a support restraining all degrees of freedom at these nodes. Now I will apply the box girder elastic links. As you can see here, the box girder has no connection with these piers. So we will provide that connection with the help of an elastic link of rigid nature. So I will use an elastic link of rigid nature and I'll define them under the boundary box girder elastic links. So as you can see, the elastic links have been generated. Now I will provide supports to the false or the temporary boundaries or the supports. I will provide only the DZ support. These are my temporary supports as I told you earlier in the presentation, and I'll assign them under the group temporary false work support. Now as you see here, there is no connection between these nodes and these supports. So I provide that again with the help of an elastic link. The purpose of showing the elastic link here is that we can model a bearing providing it certain spring constants, but to save time I am using the rigid type. So now I'm applying elastic links to connect the nodes and the supports. And similarly, I will do that on the right hand side. So as you can see here, I have provided the supports and the elastic links, but if you see here, I didn't define them under any boundary group name. For that, you don't need to redefine them, but you can generate tables, and with the help of tables, you can quickly change their group. As you can see here, all of them are in default groups. So I will select temporary elastic links. I will copy it and I will apply it to all others. So the group can be changed in the tables too. And now I will provide the elastic link supports to here so that the model can be connected through nodes. Because as I told you earlier, I have provided the supports at these nodes, and to simulate the bearing behavior here, we can use the elastic links. Again, I will use the elastic link of rigid type. I will define them under the boundary group PC girder elastic links, and I will generate the elastic links. So as you can see, I'm quickly generating the elastic links. You can also use the copy function to define one elastic link and copy them to other positions in the X or in the Y direction. But as a demonstration purpose, I will use the basic modeling features to define the elastic links. And as you can see, all the boundary conditions have been defined. Now I will activate or deactivate these boundary conditions in the construction stage definition dialog box. So in the first stage, we have to activate the false work support. I will activate the peer support, and I will activate the box girder elastic links. Also, the temporary elastic links have to be activated because they support the box girders. In construction stage number 2, under the boundary tab, I need to activate the PC girder elastic links. I need to activate the abutment supports for the girders, and in CS3, when the temporary supports are not required, I will deactivate them. So I will deactivate false work support and I will deactivate temporary elastic links. But as I told you in my presentation that in construction stage 2, the PC girders are not continuous. They are simply supported having the span length from this node to this node. So we will use the beam and release function to simulate the same. For that, I will use the beam and release. I will define them under the boundary group beam and release. I will release the I end moments and I have applied the beam and releases to these locations. And now I will activate the beam and release in construction stage number 2, and I will deactivate the beam and release in construction stage number 3, because in construction stage number 3 the girder becomes composite with the deck, and hence it becomes continuous with the structure. So in a way I have defined all the supports, and all the deactivation and activation of the supports in the construction stages have been done. Now I will talk about the load activation and deactivation. The load follows the same process as the supports or the elements follow. We define the load groups, we assign load to the load groups, and then we activate loads or deactivate loads as and when desired. Also, as I told you before, the tendon group is not required to activate or deactivate a tendon. A tendon is activated as a load. Now I will activate the required loads in my model. So first of all, I will define the static load cases. I have already defined the static load cases in terms of weight, self-weight, deck and scaffolding load for the casting of the deck, the sidewalk load, the barrier load, wearing surface load, pre-tension and post-tension loads. Now I will define the loads. First of all, the self-weight will be defined under the load case self-weight and the load group self-weight. Now I will use the element beam loads to simulate the deck and the scaffolding load, and I will assign it to deck and the scaffolding group name. Since the deck will be casted only on the precast girders, I have selected them, and now I will apply the desired load. So the deck and the scaffolding load has been applied. Now I will apply the sidewalk load. For applying the sidewalk load, I need to select the elements which are on the sides. So I go to the top view, I selected the elements on the side, and I will give them the sidewalk load. Under the group wearing surface, sidewalk and barriers and others, I have defined them under the same load group because they are to be activated at the same time. Now I will define the barriers and others load. The barrier will be on the extreme ends of the bridge, so I need to select the same elements again, and the barrier load will be activated. Under the same group, wearing surface, sidewalk and barriers and others. So I have activated again the same load for the barriers, and now I will activate the load for the wearing surface. The wearing surface will act on whole of the structure, so I will select all the beam elements and I will apply a wearing course load of minus 1.5 kilonewton per meter under the same load group. Now I will apply the pre-tensioning and the post-tensioning load. For that, as a matter of fact, I already defined them to save time, because when we define the loads, we need to select individual tendon and the jacking stress at the begin and the end, and it might take a lot of time. That's why I predefined them. So I have defined some tendons under the load group pre-tension and some tendons under the load group post-tension. So I will activate and deactivate the tendons as and when required. So now I am ready to model the construction stage loads. So I'll go to the load tab, and in the first stage I will activate the self weight. In the second stage I will activate the pre-tensioning, and the deck and the scaffolding load has already been activated as I told you earlier. And in CS3 I will apply the post-tensioning load and the wearing and the sidewalk barrier load. We can also modify it by clicking here and modifying it. So the load definition has been done and all the construction stage data for this bridge has been defined. Now I would like to tell you something about the construction stage load type that Midas Civil provides. For that I will open a previously modeled structure and I'll show you the nuance between the dead load, the static type load, and the construction stage load. So I have opened another work window of Midas Civil, and now I will open the model that I have prepared to demonstrate you the difference between the CS load and the static load. Basically, the difference is that the static loads are applied to the construction stages as well as the post-CS mode, but here in the post-CS mode the static load is applied to the last structure, and hence the results, if you compare the results from the dead loads obtained in the construction stages and the dead load obtained in defined under the static load case, will be different in the post-CS mode. While in the construction stage type load, the force effect will be accumulated through the stages and the result would be same in post-CS and the construction stages. I'll show you how. I have defined two load cases, one as static case name under the type dead load and the second in CS load case under the type construction stage load case. I will show you the different stages. As you can see here, construction stage 1, in construction stage 1 the beam is simply supported, while in construction stage 2 it becomes continuous. So if you see the results in the construction stages for the dead load, as expected, it would be the bending moment will be for a simply supported structure, but in CS2, as you can see, there is no change in the bending moment because of the addition of this support, because the results are accumulated. I will let you know in the coming slides how these results are obtained. But if you go to the post-CS mode, you can see that due to the static load case defined under the dead load case, the moment is for a continuous structure. But if you see the moment due to the dead load defined under CS dead load in the combinations, you would see that the nature remains the same. I haven't activated any load under CS2. If I activate any load under CS2, then the effect will be the bending moment obtained due to CS1 plus the bending moment obtained due to CS2. So this is the difference between the construction stage load type, that the load defined under the category other than construction stage load type will be applied to the end structure, and results will be obtained through this process for the post-CS mode. Now, since we are talking about segmental construction here, the effect of creep and shrinkage becomes very important to consider. In Midas Civil, you can consider the effect of creep and shrinkage individually. The process is to define the time-dependent material for creep and shrinkage and then assigning it to the material. The same applies to the shrinkage. The user can also define his desired creep coefficient for construction using the construction stage type load. Now I will go to the model and show you how we can define different parameters for time-dependent material properties. So either we can define the creep and shrinkage properties here. I will define the creep and shrinkage properties for the materials that I have defined. For better understanding, I will change the units to Newton millimeter. For grade C 6000, I will define the several parameters, and now I can see the creep coefficient and the shrinkage strain as required. So this is the original model that we are working on. I will define the creep and the shrinkage properties. By changing the units to Newton millimeter. The characteristic strength will be 60. I will define the notational size. I will let you know more about the notational size later. And now I will define the creep and shrinkage properties for grade C 5000. Going back to the presentation, as I told you that the user can also define his own desired creep coefficient for construction stages. The user can do that in construction stage loads and creep coefficient for construction stage. So user can define the creep coefficient for a desired construction stage. He can define it under the load group and activate it whenever he wants the coefficient to be applied. Also, the user can see the creep coefficient in the result tables for the element properties at each stage. As I told you while defining the creep and shrinkage properties, in the creep and shrinkage dialog box for the CEB FIP code, there is a term known as notational size of the member. The notational size of the member, the definition is 2 multiplied by the cross-sectional area divided by the perimeter in contact. The notational size for the beam elements can be defined in Midas Civil either automatically or using this function. The user can define the automatic properties for the creep and shrinkage, that is the notational size, by using the change element time dependent material property dialog box. So as here you can see, the user can select the code CEB FIP and he can select the beams where he wants to assign the notational size, and the Midas Civil will do it automatically for you. For the beam elements that have composite sections, the notational size is defined while defining the composite section for construction stage. As you can see here, while defining the edge, the h is defined. The program can automatically determine the value of the notational size individually for the girder and the slab. And here I would like to tell you that this value supersedes all other values defined by the user. For the plate and the solid elements, the user can define the notational size either manually while defining the creep and shrinkage properties, or by using the change element dependent material property function. But here the automatic function cannot be used. The user will have to manually calculate the notational size and assign it to the plate elements. This is an example of how the notational size can be computed. The AC becomes the area of the cross section and U becomes the parameter in contact. Also, there are some other considerations that users must understand while defining the creep and shrinkage properties to the plate elements or the solid elements. The local direction of all the elements must be aligned in the same manner, and the local x-axis of the elements, that is the plate or the solid elements, must coincide with the bridge direction. Also, in Midas Civil, the user can apply the time dependent load, that is the load which will act due to the time lag in the construction. As you can see here, segment A, which is on the left side, and segment B, which is on the right side, segment A has been constructed 100 days before segment B. So the user can model the individual stages for segment A and segment B in the same construction stage, but when the joining of these two segments will be done, the user can apply 100 days time load to segment A. Let's see how can we do that. Under the tab, load tab, construction stage loads, we can define time loads. We can assign them to a load group. We can write what time load has to be applied, how many days, and then we can assign it to a load group and activate it in the construction stage. That was about the time dependent material property for creep and shrinkage. Now, since we know that concrete achieves compressive strength, the desired compressive strength under time, so we need to define the time dependent material property for concrete compressive strength too. We can do that in Midas Civil by defining the time dependent material property for creep for compressive strength. So I will define the time dependent material property for compressive strength for the materials that I have. I will use the CEB FIP code, and here the user must understand that mean compressive strength of concrete at the age of 28 days must be entered, which is equal to the characteristic strength plus delta F, and the value of delta F remains 8. So since we know that for grade C 6000 the compressive strength is 60 MPa, but the mean compressive strength will be 68. And now I will define the same for the second material. I will use the CEB FIP again, and I will enter the mean compressive strength as 58 days. So I have defined the time dependent material for creep and shrinkage as well as the time dependent material for compressive strength. Now I will provide a link between the time dependent material property and the time dependent material. So here I'm defining the link, and the time dependent material properties have been linked to the different materials. The user can also play around with the stiffness of the section. The user can apply several factors to the area in the shear, in the Y or the Z direction, or the moment of inertia along XX, YY, major and minor axis. The user can specify this section scale factor in a boundary group and the boundary group can be activated in a construction stage as desired. So here, if the user selects a section and selects a boundary group, he can apply a scale factor to the same. Also, since we know that for the calculation of sectional stresses, the effective width has to be considered. The effective width can be considered either automatically or manually. Midas Civil provides the automatic function for ASTO LRFT code. As you can see here, by using this dialog box, the specifications defined under the ASTO LRFT will be automatically used for defining the effective widths, or the user can manually define the effective width under the effective width scale factor. The user can not only alter IY, that is the moment of inertia in the major axis, but also the scale factor for the section depth can be applied for either I or Jn respectively. The user can assign it under a boundary group and activate whenever required. The difference between the effective width and the section stiffness scale factor is that effective width is only considered to determine the stresses, and for determination of bending moments, shear force and other things, the stiffness considering the whole section will be used. While if the user defines the section stiffness scale factor, the moment of inertia and other parameters such as shear force, they will be changed as according to the section stiffness. Also here I would like to tell you about the dummy stage for obtaining results. The dummy stage, by dummy stage we mean a stage having 0 days or having infinite days for obtaining the time dependent material effect. So let's consider an example that the construction required 150 days to finish, and after 150 days the user desires to see the temperature load effect in the structure. So the user can define a load case for temperature and assign it to the temperature load case and assign it under a group and activate that load case under the dummy stage for obtaining results. I will use a dummy stage for obtaining results in my model. I can use CS4, I can name it dummy, and I can give it a duration of 1000 days just to see the time dependent material effects. Finally, let's talk about the construction stage analysis control dialog box, which is available under the analysis tab, construction stage analysis control. We will talk about these features one by one in the presentation. The user can select the final stage to be the last stage or other stage. As you can see here, I have chosen CS2 to be the last stage for analysis, and hence the analysis for the stages CS3, CS4 and so on and so forth will not be performed. The advantage of this function is that user can see the load effects for a required stage, and if there are some modeling errors, the user can run the model only till the stage where the error appears and rectify it. The user can also restart construction stage analysis from any stage as desired, but the premise is that at least one time the analysis must be performed. And let's say the user performed the analysis for 10 stages and he modifies from stage 8, so he can run the analysis from stage 8 and the results for the stages 1 to 7 will be preserved. The user under the time dependent effect control, which is available On clicking this, the user can select whether or not the creep and shrinkage are to be included. The user can also select whether the creep individually or shrinkage individually has to be included. The user can select the convergence criteria for creep analysis. The user can also select the option that the Midas Civil uses only the user-defined creep coefficient as defined under the construction stage load will be used. The user can define the internal step for creep, how many steps in a construction stage must be used for determination of creep results. Also, the user can select whether the tendon tension loss effect due to creep and shrinkage is to be determined. The rebar confinement effect can be determined. The user can select whether the time-dependent effect on the modulus of elasticity to post-CS has to be applied or not. And lastly, the user can select whether the tendon tension loss effect due to elastic shortening, which is not due to the pre-stressing loads, but all other loads other than pre-stressing loads have to be determined or not. So here, as you see, if I check on this box, Midas Civil will calculate the elastic shortening loss in the tendon due to the loads other than the pre-stressed load. If I check off this, only the elastic shortening loss due to pre-stressed load will be activated, will be determined, and all other load losses due to self-weight or live load will not be determined. The user can also perform the P-delta analysis, and the P-delta analysis can be controlled by the number of iterations and the convergence criteria. The user can also select which load cases have to be distinguished from CS dead load for CS output. Generally, the CS erection loads, the user can also select what type of load is that. So in our model, we use the wearing surface load as an erection load, and we will define it under the dead load of wearing surface and attachments and utilities. It is important because when Midas Civil automatically generates load combinations for wearing surface, it will take into account the factor as defined in the code automatically. The user can select the initial force control, whether the initial force for the post-CS has to be obtained from the last construction stage or not. It becomes very important for cable straight bridges, because in cable straight bridges for the performing of eigenvalue analysis, the geometric stiffness has to be entered, and geometric stiffness of the cable depend on the applied force. Here the user must understand that when P-delta analysis is performed, this effect is already considered. Also, if we check on the function, the option apply initial member force to CS, this member supersedes the initial forces defined by the user. The user can define the initial forces under initial forces for large displacement or small displacement, and these initial forces can be used for geometric stiffness for cables. The user can also select whether or not the tangent displacement to erected structures is to be determined or not. It becomes very useful in the construction of structural steel bridges and precast members, and it is related to fabrication camber. In large displacement analysis, this function is already considered by default. So this is an example showing how the initial tangent displacement to erected structures will be applied. So let's say this is the new segment that has to be added to this part, and because the node at which it has to be attached has already deflected, it has some rotation, it has undergone some rotation due to the dead load and other loads. So this would be the profile of the segment. It becomes very useful for the determination of fabrication camber. The user can also select how the stress will be transferred from the tendon to the beam. So the user can select whether it would be a linear interpolation or a constant stress. The user can select whether the beam section property changes with tendon or remains constant. Also, the user can select the output for the current stage or not. Finally, the user can save results individually for a stage or additional steps. The additional steps, as I told you before, are defined under this tab. So let's now open the analyzed model for finding the results of the modeling of the spliced girder bridge. So this is an analyzed model that I previously analyzed, and now I will show you the construction stage results using this model. The model contains entirely same construction stages with the same elements, loads, and boundaries. The construction stages results are shown under these categories. The CS dead load, which comprises of the loads defined under the static load cases, such as the dead load of attachments, wearing surface load, temperature loads, and all other loads. The CS erection load is the load which is defined in the construction stage analysis tab that I told you before. We put the wearing surface load into this category, and we can see the effect of the wearing surface load under the erection load. The CS tendon primary will show you the primary effect of the tendon pre-stress load on the structure. The CS secondary, tendon secondary, will show you the effect of the tendon pre-stressing load on the indeterminate structures, because we know that in indeterminate structures the tendon causes secondary forces. Similarly, the secondary forces and primary forces due to creep and shrinkage are determined, and you can see the individual effects of them. Lastly, the CS summation for reaction, deformation, and force is different. This table is available in the online manual, and the user can refer to it as and when required. Secondly, the deformation that are obtained in the default mode, that is, if we obtain the deformations by clicking, let's say we go to CS2 and we want to know the deflection due to dead load. So as you can see here, the structure has deflected in this manner due to the dead loads. And we haven't selected, this is the default mode, we haven't selected any other thing. So here I would like to tell you how this deformation is obtained. This deformation is obtained by adding the deformation obtained due to loads in CS2 by adding it to the deformation obtained in CS1. So it is an accumulated deformation, and it is not that all the loads up to CS2 are applied on the structure in the CS2 and then the deformations are obtained. The deformations are obtained individually for the loads defined in CS1 and CS2, and the effect, the deformations, will be accumulated. The user can also see the deformation due to the current load, the current step load, by selecting this option known as current step displacement. So if I activate this option and click on apply, you can see the deformation due to the current step. So let's go to the CS3 and see the deformation. So as you can see here, the default deformation has this profile, and the deformation due to the current step load is this. Again, as I told you that in Midas Civil you can see the tangent displacement because of the rotation of the node. So here I would like to demonstrate how that deformation is obtained. If you select the option stage step real displacement, it shows you the initial tangent displacement. So let's see how it is done. As you can see here, this cantilever is constructed in 3 stages: segment 1, segment 2 and segment 3. When the segment 1 is constructed, it undergoes a deflection and rotation at this point, which will cause the deflection delta 21 when segment 2 is constructed and delta 31 when segment 3 is constructed. And when we construct segment 2, it undergoes more deflection due to its own self weight and causes the new segment that has to be added another deformation, that is the tangential deformation. And when segment 3 is activated, it undergoes on its own deformation. So this is how the initial tangent displacement is calculated, and we can see it by checking on stage step real displacement. It is especially important in balanced cantilever bridges, in incremental launching bridges, etc. Also, the beam diagrams, the force and the bending moment diagrams that we obtain are accumulated. That is, the bending moment obtained at CS1 will be added to bending moment obtained at CS2 loads, and third, and so on and so forth. So again it is accumulated. So if we see the beam diagrams for MY in CS1, so as you can see how the beam diagrams are produced. So as I told you before that in construction stage 2, the girders will be simply supported, and as you can see here, the bending moment obtained in construction stage 2 is the one obtained for the simply supported beam. If we see the bending moments due to CS3, as you can see how the bending moment changes because the deck becomes composite with the girder, and we see negative bending moments at the interfaces. The same criteria that I told you, that the accumulated beam bending moment diagrams are obtained. The stresses can also be obtained for the individual steps of construction stages. We can see the stresses in a variety of manner. We can see the stresses for PSC beam at 10 different locations and for different components. And we can also see the stresses due to in the individual parts of the composite beams. So as you see here, you are looking at the stresses in the first part, the first component, and if you select part 2, you can see the stresses in the second component, that is the deck. As I told you, stresses for different parts can be calculated. The user can also generate the tendon time dependent loss graphs. I would like to interrupt here, and I would like to tell to the users, those who are sending questions, that I would entertain their questions towards the end of the webinar, and there is a separate time for that, and you can keep sending me the questions, but I would reply to you only after the webinar completes. So this is how the user can calculate the tendon time dependent loss graph, and we can also animate it. So let's say we have to generate the tendon time dependent loss graph for a tendon which is activated in a construction stage. The user can also generate the tendon loss table. The user can select the tendon that is activated in a construction stage, and the user can see the stress due to immediate loss. And I would like to tell you more about the individual losses in the coming slides. So for the pre-tension, I have compared the loss in the pre-tension and the post-tension. The friction loss is considered in post-tension, anchorage in post-tension, and the elastic shortening loss is considered in pre-tension. But the elastic shortening loss due to staged post-tensioning can be considered in post-tension girders. The creep and shrinkage loss and the relaxation loss is considered in both of them. So this is a table that is generated when the user select the tendon table for the tendon loss. As you can see here at the top, there are several different columns. The first column is stress after the immediate loss, A. The immediate loss A in post-tension beams is calculated because of the friction loss and the anchorage slip loss. And in pre-tension beams, it is calculated only for the elastic shortening loss due to the pre-stressing load and not due to the self-weight or other live loads. This is how the anchorage loss is calculated in the post-tension girders. The anchorage loss is 2 multiplied by P multiplied by L set. Here P is the frictional resistance per unit length determined by the friction loss between the anchorage and the quarter length of the beam divided by the beam length divided by 4. And the friction loss is calculated using this formula. For more information on anchorage loss and friction loss, the user can refer to the analysis manual or the online manual. The user can also see the elastic deformation loss B, which is due to the other loads. The other loads includes all those loads apart from the pre-stressing loads, that is the self-weight, live load, creep and shrinkage, etc. And the elastic shortening due to staged post-tensioning loss can also be seen in this column. So as you see here, there are two tendons. First tendon is pre-stressed, and after pre-stressing first tendon, the second is pre-stressed. So as you know that when we pre-stress this tendon, the second tendon, the first tendon will undergo some elastic deformation, the elastic shortening, and hence there would be some tendon loss. The user can see the creep and shrinkage loss under the creep and shrinkage loss column. The user can see the relaxation loss. The relaxation loss in the CEB FIP code is determined by this formulae. The user needs to enter the percentage of relaxation after a long period of time, and the initial stress is calculated after the instantaneous losses, and gamma is entered by the user while defining the tendon properties. So this is, if I use the CEB FIP code, the user must define the percentage of relaxation coefficient which is used for the determination of the tendon loss for the relaxation. And finally, the user can also generate the stage step histograph. The stage step histograph can show you the change in the bending moment, shear force or deformation or any other stress with different construction stages. So let me demonstrate you how is it done. So let's say we want to see the bending moment at a node So I will name it moment, and if I select this and the load combination for which I want to draw the diagram, I can see how the bending moment changes with different construction stages. The user can also see the element properties at each stage, which becomes very useful to see the elasticities, how the elasticity changes along with different construction stages. So if we go to result tables and the construction stage, we can see the element properties at last stage or individual stages by selecting the stages, and we can see the elasticities, the shrinkage, the creep coefficient that have been taken for the determination of creep loss and creep deformation. And the user can also generate the tables for the same. Let me demonstrate you how the tables can be generated. Let's say the user wants to see the bending moment diagrams used for the dead load, and he wants to generate table. So let's say the table from element 51 to 81 are desired due to dead load in construction stage 2 and 1 for different parts I and J. So the user can generate the tables as required, and by right clicking, the user can play around with the records again. So in all, in Midas Civil, the base stage is for the modeling of the construction stages. The min-max stage, if you analyze the program, you will see that a min-max stage is constructed, and in this min-max stage, when you see the diagrams or anything, the effects will be due to the maximum effect generated in any of the construction stage. So it might happen that the bending moment on a particular element is maximum in CS5, but there are 20 stages, so this option will show you the maximum moment at any point of time in a segment. And the post CS mode is when all the loads are applied to the element, to the whole of the structure. Finally, the user can generate the load combinations, and the user can generate the load combination for only static loads or only CS loads or static plus construction loads. So the user can auto-generate load cases for ASTO or Indian or Euro codes and Taiwanese code and several other codes, and the user can select whether he has to obtain the static load cases only or the CS load cases or static plus CS both. So this ends the webinar for the construction stage analysis. I hope you enjoyed the webinar, and now I will entertain the individual questions asked by you guys, and I would like to answer them. So you can ask questions using the chat window. So there is a question from Mr. Solis Anusus. He asks, elastic link garden nature, how do they work and what effect do they have on the construction? So as I told you before, sir, that elastic links are particularly important to model the bearings, and we know that the bearings have certain stiffness in the X, Y and Z direction and also some rotational stiffness. The user can use these stiffness to model the bearing. Or if you talk about the ballast in the railway bridges, The user can also specify the multilinear characteristic of the ballast for the axial forces. So it becomes particularly important for the bearings and the modeling of the ballast. I hope it answers your question, Mr. Solius. If you have more question on this, you can send me the question again to the chat window. There is another question by Mr. Airy. He says, when we have pre-stressed tendon modeled inside the element, the area transformation will be calculated automatically by Midas. Yes, as I told you before, that if you select this option, the beam section property, the change or either remain constant with the change with tendon or constant option. So if you select constant, no change will be affected, but if you select change with tendon, the change will be there after the definition of the tendons. There is another question from Mr. Chia Hun Lin. He says, what is the difference between the rigid link and the rigid elastic link? Well, in principle, there is no difference between rigid link and the rigid elastic link, but the elastic links, there are certain internal calculations that program can perform with either rigid links or elastic links, such as if you want to deactivate any rigid link in a construction stage, you cannot do that, and hence the deactivation, if you want to deactivate a rigid link, you can apply elastic link of rigid nature to simulate that process. I hope it answers your question, Mr. Chia Hun Lin. But if you send me an email at esupport@midasit.com, I can give you more detailed explanation about the same. There is another question from Mr. Loria. He asks that in the previous version we could define a combination among CS loads, and we can see that combination in different CS stages. Now it is not possible. As I told you before, you can define the combinations using the static load only, or the CS plus static loads, and you can see the effect of these combinations in the post CS mode only. So if you have any more questions, you can send me the questions to the chat window, and I will be more than happy to answer your questions in the real time. I would like to notify here that the recordings will not be distributed for this webinar, but the presentation can be mailed individually if you ask for the same. There is a question from Mr. Airy. He asks that he has to model an external tendon for concrete arch bridge during construction, and later the tendon becomes an internal tendon. So how can he model it? So for modeling the external tendon, you can select the tendon type as external here. But if you want to make the tendon internal, then you have to model another tendon and deactivate the previous tendon and activate second tendon, which would become internal during the construction stages. So you can do that by first defining the tendon to be external and then defining another tendon having the same profile but with internal, that is pre or post tension, and deactivating and activating the same. The question asked by Mr. Lee Pong Hong. He asks, what is the composite section for construction stage? The composite section for construction stage is a dialog box with which you can define when the deck becomes composite with a girder. As you can see here, this is a girder and this is a deck, and this represents a composite section, and they will be connected using stiffeners. So for modeling that, in Midas Civil, you can model when the deck becomes composite with the girder by using this composite section for construction stage dialog box. There is a question by Mr. Ari again. He asks, can we perform earthquake analysis with construction stage analysis? Yes, we can do that. Let's say at the end there are 10 construction stages and you want to see the earthquake analysis results after construction stage 5. So by running the model till construction stage 5 and defining the earthquake response spectrum loads, you can see the effect in the post CS till CS5 only. So earthquake with construction stage analysis is possible. So there is another question asked by Mr. Anna Loria. He asks, when we define the tendon grouting, it refers to nth stage after the one in which it is defined, or it is related to the global process. So I would like to comment here that the grouting, if you define the grouting here after 2 stages, let's say, then the grouting will be relative to the activation of the tendon. So when the tendon load becomes activated, the grouting will be done 2 stages after that activation. So there is another question by Mr. Lee. He asks, should the activation of composite section and deactivation of wet concrete loading defined in the same data in the construction stage? 3, say 10 days, or it doesn't matter what is the exactly data. So I think your question revolves around this construction stage 2, in which the girder is not composite with the deck, but on the 10th day, the deck has been casted. In CS3, the deck becomes composite with the girder. So, if you define the composite section for construction stage here and you give it an age of 7 or 21 days, it supersedes the age defined under the construction stage definition box. I think this is what is your question. If it is not answered properly, you can again send the question. So there is another question by Mr. Johar. He wants to ask, did the seismic forces been involved in construction stages? If you model the seismic forces as nodal loads or element beam loads in the desired direction, you can apply those loads in the construction stages, but you cannot perform the time history analysis or the dynamic analysis in the construction stages. But the other way is to do the time history analysis or response spectrum dynamic analysis for a construction stage by running the model till that stage only, and then in the post CS mode you can see the effects due to the time history. So as you can see here, if you select the final stage as CS2, the program will do the analysis till CS2 only, and in the post CS mode then you can define the time history analysis load case, and that analysis, dynamic analysis, response spectrum analysis can be performed. I hope it answers your question, Mr. Johar. There is another question by Mr. Darwin Chandra. He asks, if we define construction stage boundary as original type, is there any additional force, and what is the effect for the structure and boundary support reaction? Mr. Chandra, as I showed in my presentation, that if you select the original type as in the activation of the boundary, Midas Civil first brings the structure to the non-deformed level by applying force, and this is like applying specified displacement of supports load. So this is how internally the calculations are performed in Midas Civil. So if you define, let's say the structure has deformed to about 5 millimeters while reaching the support. Let's talk about the Allen bridge now. So the Midas Civil will apply a force in the reverse direction to bring it back to non-deformed shape, and then this is how the analysis is performed. So there is another question asked by Mr. Anna. He asks, is there any other way of changing the boundary applied to the model without doing a CS analysis? Yes, we can do that by applying boundary change assignment to load cases and analysis. So in this dialog box, you can apply which boundary group you want to select for which load case. There is a question by Mr. Eddie. that he wants to do the FRP strengthening of the beam and how he can model it in Midas Civil. So as I told you in my presentation, you can use the section stiffness scale factor. So let's say after a certain point of time you did the FRP strengthening, so you can define modified stiffness of the beams under this boundary group, and you can activate the bounding group in the stage when the FRP strengthening is being done. And then Midas Civil automatically updates the stiffness of the sections, the stiffness of the beams, and the effect can be seen. There is a question by Mr. Lee Pung Hung. He wants to know how the moving load effect can be put on a lot of elements. So when we define a moving load, we define a lane first. So while defining the lane, the user can select on which element the lane will be defined. So let's see here, I define the lane on these as elements. So it contains a number of elements. So the effect can be seen on these elements. I hope it answers your question, Mr. Hung. Yes, the partial pre-stressing, as asked by Mr. Airy, that can we do the partial pre-stressing? Yes, partial pre-stressing can also be done. You can apply different pre-stressing loads in different construction stages, and this is how it is possible. There is another question by Mr. Anna. He asked, is it possible to analyze a composite section with GST? Yes, we can analyze a composite section with GST. We can assign different materials to different shapes in GST, and this is how we can analyze a composite section with GST. The question asked by Mr. Shalom that usually in pre-stressed pre-tension cables we neutralize the strands at the end of the girders by isolate the strand from the concrete using pipes. Is it possible to do that in Midas Civil? Yes, we can do that in Midas Civil by defining the tendon type as unbonded, and by defining this you can simulate this real behavior. There is a question by There's a question from Mr. Anosus. He wants to know, can you explain in section data what slab width and girder number works, how can we enter the width? So while we generate, there are two cases. Let's talk about the bridge, the splice girder bridge example that I have modeled here. So it contains 9 different composite sections and there is a deck on the top of it. So while calculating the IZZ for the deck, we need to enter the total deck width here in BC, in the slab width and the number of girders. So while the program calculates the IZ, for the grillage model, the user must enter the same data, that is the data for one section only. So slab width would be the width for a section and the girder number will be 1 having CTC 0. I hope it answers your question, Mr. Salius. There is another question asked by Mr. Ari. Can Midas check the ultimate capacity of the pre-stressed beam automatically? Yes, Midas Civil can do the design check, and Midas Civil can perform the design check using ASTRO LRFT and Eurocode, and it automatically generates the ultimate bending resistance for both the codes. So there is another question asked by Mr. Hung. He wants to ask whether this model or section considers the transverse stiffness of the bridge deck. So as I told you before that I have modeled some cross beams so that the rigidity of the deck in the transverse direction can be seen. So these cross beams, they have been modeled to provide the structure, the transverse rigidity of the deck. I hope it answers your question, Mr. Hong. There is a question by Mr. Alex. He wants to ask whether in unbounded cables we use for the whole length of the beam, especially in post-tension beam. He wants to ask whether he can separate only part of the tendon from the concrete. So we cannot do that. We cannot assign a same tendon bonded or unbonded behavior both, but individual behavior can be assigned. I hope it answers your question, Mr. Alex. If you have any more questions, you can send me the questions using the chat window. So I satisfied your expectations with the advanced webinar. If you have any more questions, you can send me the questions at esupport@midasit.com. This is the email ID at which you can send me individual questions, and I would be more than happy to answer any of the technical query asked by you regarding Midas Civil. Thank you very much for attending the webinar. I hope you had a great day ahead.